Carbon dioxide concentration in the atmosphere doubled since the Industrial Revolution from 280 parts per million to 440 parts per million in 2021. While carbon dioxide is naturally present, human activities, especially from untreated flue gas emissions, contributes to the rise on greenhouse effect leading to climate change and environmental damages. The gas from industrial combustion contains up to 15% carbon dioxide. Conventional CO2 capture method includes amine scrubbing, which make uses of 30% MDEA. Despite being used in the industry, 30% MDEA possesses drawbacks of its own, which includes high regeneration energy, solvent degradation, corrosion issues, and non-biodegradable. The corrosion issue is caused by the high moisture content present in the post-combustion flue gas. Many efforts have been made to find an alternative to using 30% MDEA due to its drawback, which is why ionate liquids have been the interest in many studies as it is low melting salts with unique properties like low volatility, high stability, as well as strong solventing ability for CO2 capture. However, ionate liquid possesses its own drawbacks as well, which hinders the application to the industry to this day. Among ionate liquids' drawbacks are it is expensive, difficult to synthesize, and it is non-biodegradable, which is why another solvent is studied, which is deep eutectic solvent. Deep eutectic solvents are a type of solvent formed by mixing two or more components, typically a hydrogen bond donor and a hydrogen bond acceptor, which interacts through a hydrogen bonding. This interaction lowers the melting point of the mixture below that of its individual components, creating a stable liquid at room temperature. Deep eutectic solvents share properties with ionate liquids, which are thermal stability and low volatility. However, deep eutectic solvent possesses more advantages compared to that of ionate liquids, such as cheaper, easy preparation, biodegradability, and better stability in humid conditions. Which is why the objective of this research is to confirm the formation of hydrophobic deep eutectic solvent through characterization using FTIR and DSC. And second, it is to analyze the hydrophobicity using a goniometer to measure the contact angle. Lastly, it is to evaluate the performance of CO2 absorption using a CO2 solubility cell. Chemicals used for this study are thymol, EDA, TEPA, DETA, pH, and theta. The preparation of Thymol-Amine starts with thymol being weighed according to 1:1 molar ratio and placed into a vial. Each amine was then measured and then added into the vial containing the thymol. Then, the mixtures was then stirred at 60 degrees Celsius using a magnetic stirrer until a homogeneous liquid is formed. Now, moving on to the characterization of DES. FTIR was used to confirm DES formation by detecting hydrogen bonding and shift in key functional groups indicating strong intermolecular interactions. Shown here is the FTIR spectrum obtained for both reagents and mixtures formed. According to the data interpreted, OH and NH stretching shows the strong hydrogen bonding between thymol and amine for all the mixtures. This confirms the DES formation. The stretching of CN and CO at 1000 to 1300 shows the intermolecular interaction, which further supports the formation of deep eutectic solvent. Differential scanning calorimetry was used to analyze the melting points of individual reagent and the prepared mixture to construct a binary phase diagram. This analysis helps to identify any shift or depression in melting point, which serves as a key indicator of deep eutectic solvent formation through strong intermolecular interactions. According to the obtained melting points for reagents and mixtures, a binary phase diagram was constructed to determine the conformation of the true deep eutectic solvent formed. Based on the binary phase diagram, the only true DES formed at 1:1 molar ratio is thymol-EDA, as it formed a deep eutectic depressed melting point. This is possible due to the melting point of thymol-EDA is much lower than that of its reagent, which are thymol and ethylene diamine. Goniometer will be used to assess the hydrophobicity of the prepared mixture to indicate the hydrophobicity according to the contact angle and wettability. Here shows the result obtained for the hydrophobicity of the mixtures prepared. According to the data obtained, it was confirmed that thymol-EDA is the most hydrophobic mixture compared to the rest, as it exceeds the hydrophobic line, which is obtained from the literature work of a hydrophobic deep eutectic solvent. On the other hand, a carbon dioxide solubility cell was used in this experiment to determine the absorption capacity of the prepared mixture, and above shows the formula and schematic diagram of carbon dioxide solubility cell. According to the data obtained, it was proven that the highest CO2 absorption belonged to thymol-EDA as compared to the rest of Thymol-Amine mixtures, where it has an absorption of 2.79 millimole per kilogram. Now, this research contributes to the SDG, which is first, SDG 7, affordable and clean energy, where hydrophobic Thymol-Amine DES offers a potentially more efficient and lower energy alternative which reduces the energy required for regeneration. Next, unlike conventional solvents, DES offers a biodegradable properties, less toxic and environmentally friendly as it makes uses of thymol, a naturally occurring material from thyme leaves. Not only that, but DES can enhance carbon dioxide absorption. Without the excessive water uptake due to the hydrophobicity, this improves the efficiency and long-term stability. Another SDG which this research contributes to is the SDG 13, Climate Action. Hydrophobic Thymol-Amine DES provides a potential solution to capture carbon dioxide efficiently, which helps industries lower their carbon footprint. Other than that, effective carbon dioxide removal is crucial for slowing down global warming and achieving climate goals. By improving the carbon dioxide absorption efficiency, this will help combat the global warming issue. Lastly, SDG 9, Industry, Innovation and Infrastructure. This project contributes to the advancement of carbon capture technology where hydrophobic Thymol-Amine DES introduces a new efficient and less energy-intensive approach for industries. Moreover, developing a new approach to the carbon capture represents a step forward in environmentally friendly chemical engineering. To conclude, the best Thymol-Amine mixture to be considered as deep eutectic solvent is found to be Thymol-Eda due to its highest hydrophobicity, highest carbon dioxide absorption capacity, and is the only confirmed deep eutectic solvent at 1:1 mole ratio. For this research, it is to recommend a further optimization of Thymol-Eda composition by adjusting to the molar ratio to enable potential ideal composition that maximizes efficiency. With hopes in this potential greener solvent to be used as a future of CO₂ capture, this may be a stepping stone to combat the global warming issue.